Hello! Today we are going to look at exponents and exponential functions. And to start with, we will take a look at an exponential function form like we might see here. Y equals a times b to the x. A few things to look at here in terms of the anatomy, if you will, of this. So for starters, right here, this part, b, this is your base, just like we've seen with exponents before. What makes this an exponential function, however, is quite specifically this x. This is the exponent, and this is where the variable is. So if I had y equals 3 times 4 to the x, this is an exponential function because I have x right here in the exponent. What is not an exponential function is if I have something like y equals x squared. No, that is not an exponential function because your exponent is a constant. It is a number. That does not change. It is not a variable. So that is separate. That is not an exponential function. So we want to keep in mind that our terminology here, I've got the base. In this case, for my example, y equals 3 times 4 to the x. What is the base? The base would be this 4. And what is your exponent? Again, that's where the x is. Quite technically, you could have something else up there as well, like times it. So you could have, if you wanted to get fancy, y equals 3 times 4 to the 2x. That's possible, but at the end of the day, what makes the function an exponential function is the fact that your variable is in the exponent. All right. So we could see something like, let's look at another exponential function here. Y equals, let's say, 2 times 3 to the x. We can make a table because tables are good things. When in doubt, make a table. If I plug in 0, then I've basically got y equals 2 times 3 to the 0, and that's anything to the 0 is just 1, so y equals 2 times 1, I get 2. If I plug in, similarly, if I plug in 1, I'm going to get 6, because 2 times 3 to the 1, in other words, 2 times 3 equals 6. If I plug in 2, that's 2 times 3 squared, which is 2 times 9, I get 18. If I plug in 3, that's 2 times 3 to the third, which is 2 times 27, which would be 54. So we see that exponential functions can increase, and they also can decrease quite rapidly. So, for example, if we take a look at this guy right here, here's that function. Here is 2 times 3 to the x, and we see it starts right around 2 when you plug in x equals 0, just as we expected. And wow, by the time it's already at, that's about 2 right there, where it's about 9. It is 9 on the graph, it's just a little tough to see. And we see it just skyrockets. And it all connects to, check this out. If I go from 2 to 6, what operation can I do to change the value from 2 to 6? And to go from 6 to 18. And to go from 18 to 54. Well, the secret is in the big factor of why exponential functions work, and what they are is you're just multiplying by 3. So times 3, 2 times 3 gives me 6. 6 times 3 gives me 18. 18 times 3 gives me 54. If I wanted to know what 4 would be, without doing really any other calculations, if this is the pattern, then I can just think of, oh, 54 times 3 gives me 162. That's what this exponent is. Remember, if we expand this, if we expand 2 times 3 to the x, let's plug in a number there just to see. 2 times 3 to the 4th, if we write it in expanded form, this is 2 times 3 times 3 times 3 times 3. I have 4 3's. Compare that to 2 times 3 to the 5th, which is almost the same thing, except now I've got 5 3's. So the difference between, if we wanted to go from this value up here to this one down there, multiply it by 3, because you've got one more 3 down here than exists up there. That's what keeps changing. That's what exponential functions are. You keep multiplying by a number. Compare this to, with a linear function, we might have y equals 3x plus 2. If you make a table with that, if I plug in 0, I get 2. If you plug in 1, I get 5. If you plug in 2, I get 8. The pattern here from 2 to 5, from 5 to 8, you're adding 3. Add 3. So where linear functions add, as in the sequence, your exponential functions are really multiplying. And you can see this sometimes when you're looking at data, when you're looking at a table. So if I have something like this, if I've got two sets of data, I've got 0, let's say I've got 1, I've got 1, I've got 10, I've got 2, I've got 100, I've got 3, I've got 1,000. We start to see the pattern here. How would you describe it? Well, I've got 1 here to go from 1 to 10, from 10 to 100, 1,000 to 100. You can take one term divided by the previous term. 1,000 divided by 100 equals 10. The same thing holds from here to here. 100 divided by 10, whoops, sorry, my zeros are disappearing there, gives me, gives me 10. Divide one term by the previous term to find out what the change is. In this case, I keep multiplying by 10. So I could have y equals, my base here when I plug in 0 is 1. 1 times 10, this is what I'm multiplying by. I keep multiplying by 10, so that will be my base to the, let's try to the x. In this case, this works very nicely because 10 to the 0, 1 times 10 to the 0, well 10 to the 0 is just 1. So this is really 1 times 1 equals 1. This is our, again, this is our x, there's our y. And I can test it out again. I've got, if I have 1 times 10 to the 1, then I get 10. 1 times 10 squared equals 100. Those are zeros. All right. So this is what we are looking at right now. We will explore. We will see a little bit more about how these work in how incredibly useful these are. So there's a lot of stuff here. Go back, take a look at it, bring in your questions, and have a fantastic day.